Good day everyone, I am Ingdasun.
I am Aljayu.
I am Ines Irdina binti Fauzi.
And I am Nabiha.
We are from Group 5.
In this webinar, we are going to show you how to conduct the Equilateral Triangle Diagram,
Which is related to math transfer knowledge.
This video is long, but please be patient to watch this video so that you can learn something from this video.
So let's get started. Here we go.
Alright, so let's begin our webinar. Our topic for this webinar is the Equilateral Triangle Diagram, which conducted and presented by Group 5. In this webinar, we are going to talk about the objectives of the webinar. We will show you the procedure on conducting Experiment 1 and Experiment 2. We are going to discuss the results and discussion, and we are going to conclude the whole lab that we conducted.
Hello guys, before we go into the experiment, let me discuss our Equilateral Triangle Diagram. The Equilateral Triangle Diagram, developed by Hunter and Nash, is commonly used for multi-stage extraction calculation in the binary system. In practice, toluene is used as a solvent to remove the solid acetone from water. The toluene-rich phase is called the extract, and the water-rich phase called the refinate. The solubility curve is obtained experimentally by Claude point iteration. Water, for example, is added to a mixture solution of toluene and acetone, and it's noted that one side of cloudiness due to the formation of a second phase equivalent. The mixture is 10% of water, 26% of toluene, and 64% of acetone by weight. In order to obtain data for construction timeline, it is necessary to make a ternary mixture, such as 30% of toluene, 50% of acetone, and 20% of water by weight. Equivalent it by agitating the mixture for at least 90 minutes. Then let the mixture to settle in a separating funnel into two distinct clear layers with a sharp interface. The resulting extract and refinate phase are analyzed by using spectrometer. There is two main objectives of this experiment. For experiment 1, to obtain the binary or solid curve for both water and toluene-rich phase. For experiment 2, to determine the tie lines connecting the binary curve obtained in the experiment above. Now we are going to discuss about the theoretical background. First, we have to know about liquid-liquid extraction. The separation by liquid-liquid extraction can be defined as the selective removal of one or more components either from a homogeneous liquid mixture or from a solution using a second liquid or solvent, which is partially or wholly immiscible with the first. A widely used terminology describes the system in the term of FSRE, which is F means feed, S means solvent, R means refinate, E means extract. Each stream consists of two components. The feed streams consist of the required component and solvent. The refinate stream has the same component as the feed, though the proportions are different. On the other hand, the extract streams consist of the required component and solvent. The difference between the extract component and the extracting solvent or extractors may be clear. Now we need to know what is solid, solvent, and dilute. Feed is a two-component system. By convening, the material to be extracted is commonly referred to as a solid, while the other component is generally referred to the dilute. The refinate as the same component as the feed. Hopefully, it is much less concentrated in solid. Instant example, it is said to be a linear. An ideal unit with perfect extraction given refinate which has one component only, that being pure dilute. The liquid used to strip the solid from the feed is referred to as the solvent. However, solvent is a general term and can sometimes be confusing, as for example by describing the diluent as the feed solvent. The term feed solvent should then be avoided. The solvent after becoming enriched in the solid leaves the system as the extract. It is also important to define the composition of the post stream, and this may be done in several ways. And the most familiar way is the molar concentration, model concentration, molar fraction, mole fraction, mole ratio, mass fraction, and mass ratio. Note: the fractions and ratios are dimensionless. Fraction and ratio may also be expressed as percentage.
Alright, now we are going to explain the theory of the equilateral triangular diagram. Since the liquid-liquid extraction generally involves a three-component system, therefore a graphical representation of the liquid mixture is usually employed. There are two types of graphical systems, which are the rectangular coordinate and the triangular coordinate. As you can see, this is a typical three-component system representation on equilateral triangular diagram. And the three vertices, which namely A, B, and C, are represented by the solvent, diluent, and the solute. However, they might be come across with literature assigning the symbols differently, but you shall not confuse as long as the apex is the solute and the bottom two vertices are the solvent or diluent. The curve on the diagram is called the binodal solubility curve of the ternary system. The curve is essentially a combination of diluent-rich and solvent-rich curve. Separates the upper region of stable single-phase mixture from the lower region of unstable mixture, which tends to separate to give extract and raffinate. P is a plate point, E1 is the extract, and R is the raffinate. The composition of extract and the raffinate are connected by the tight lines, and they are having different slopes. The tight line will get shorter as they are get away from the x-axis, and eventually they will finally converge to a P point, the plate point. And for your information, the plate point is not normally the highest part of the curve. After that, this is the tight line construction for determination of HETS, the height of equivalent to one theoretical stage. The number of theoretical stages can be determined graphically by constructing the tight lines. As you can see in the graph, the E1 is connected to R1, E2 will connect to R2, E3 connect to R3, and E4 will connect to R4. And then the height equivalent to one theoretical stage is determined by dividing the effective column height with the number of theoretical stages.
Hello there! So now I'm going to explain about the procedure of the experiment 1, which is the determination of binodal or solubility curve. The apparatus that we need to use in this experiment 1 is the beakers, the measuring cylinder, the titration apparatus, and also the refractometer. In this experiment 1 also consists of two phases, which are the toluene-rich phase and the water-rich phase. So for the first one, the toluene-rich phase. The first step is we have to prepare at least 6 different homogeneous mixtures of acetylene and toluene in the beakers first, then transfer it into the conical flask for titration process. The second step is place the conical flask into a hot plate and place a magnetic stirrer into the mixture, then titrate the mixture using water. The third step is slowly titrate the mixture using the water until cloudiness and precise in the mixture. To ensure the titration process is complete, the cloudiness of the mixture must retain in the conical flask at least for about 5 seconds after the titrate. Record the amount of water that has been added into the conical flask. The fourth step is take about 10 ml of the titrate products. Repeat the step 2 and step 3 using the other mixture that we have prepared. For the fifth step is measure the refractive index of the 10 ml that we have taken from the titrate product using the refractometer. So, for the water-rich phase, the step is almost the same, but we have to prepare at least 6 different homogeneous mixtures of acetone and water and place it into the conical flask. The second step is the titration process. In this water-rich phase, we will titrate the mixture using the toluene instead of the water. The third step is slowly titrate the mixture until cloudiness and persist in the mixture. And again, to ensure the titration process is complete, the cloudiness of the mixture must retain at least for about 5 seconds after the titration process. Record the amount of the toluene that has been added. The fourth step is take about 10 ml of the titrate products. Repeat step 2 and step 3 using the other mixture. The fifth step is measure the refractive index of the 10 ml that we have taken from the titrate product using the refractometer. Lastly, don't forget to take the average temperature of the mixture during the experiment. Next, my friend will continue to explain the result that we can get from the experiment 1. Thank you for listening.
Now we're going to discuss the result for experiment 1A, which is the toluene-rich phase. This is the data which we obtained from the experiment. From here, we can know that experiment 1A was showing the composition of the light phase. From the data which we obtained, we can plot the graph which is refractive index against the weight of acetone. From here, we can know that the value of refractive index is decreasing by the value of the weight of acetone. In other words, we can say that the value of refractive index is increasing by the weight of the toluene. The equation that we obtained from the experiment will be used in experiment 2. Now we're going to discuss about the experiment 1B, which is the water-rich phase. This is the data which we obtained from the experiment. From here, we can know that experiment 1B was showing the heavy phase composition. From the data we obtained, we can plot the graph which is the refractive index against the weight of acetone. From here, we can know that the value of refractive index is increasing by the weight of acetone, and the equation that we obtained from this graph will be used in experiment 2. Now we are going to draw the binodal curve for the experiment 1. The right hand side will be the experiment 1B and the left side will be the experiment 1A. So now we're going to plot the curve which is look like this, and the equation that we obtain from this will be used in experiment 2.
Hi everyone, I'm going to present experiment 2 for determination of equilibrium solute distribution or timeline. At the two-phase region, there are timelines that connecting the composition of raffinate phase and extract phase. Objective for experiment 2 is to determine the timeline connecting the binodal curve obtained in the experiment. apparatus for this experiment are conical flask and separating funnel for settling separating the solution, then beaker, measuring cylinder, and refractometer. Now let's proceed to the procedure for this experiment. First, fill in the conical flask with the heterogeneous mixture of water, acetone, and toluene. Prepare 6 mixture with different composition. The table shows 6 mixture with different composition. Then, agitate 6 mixture with different composition in step 1 at least 90 minutes. For step number 3, after 90 minutes, stop the agitator and transfer mixture in conical flask into separating funnel. Let the mixture to settle for about 1 hour in a separating funnel into 2 distinct clear layers with a sharp interface. For step number 4, we draw a sample for each phase and measure the refractive index for each phase. Again, take an average of 3 readings for each phase. The water-rich phase, or known as refinate, would be heavy phase, and toluene-rich phase would be the light phase, or known as extract. After that, repeat step 4 for all of the heterogeneous mixture. The calibration curve prepared in experiment 1 can be used to determine the composition of acetone in each phase determined in step 4 and 5. Y is representing refractive index. X is representing weight of acetone in heavy phase or light phase. Calibration curve for experiment 1A can be determined the composition of acetone in light phase, and calibration curve for experiment 1B can determine the composition of acetone in heavy phase. For step number 7, draw the tie line connecting the extract and refinate using the composition determined in step 4 and 5. This tie line must pass through the total mixture point M based on the amount added in step 1. For step number 8, measure the average temperature during your experiment. The temperature can be measured when we measure the refractive index. This is the picture during our group conduct this experiment. So, mixture of solution agitate for 90 minutes at 90 rpm. So this is mixture we left to settle in separating funnel until 2 distinct clear layers with sharp interface observed.
Okay, after my groupmate Nabiha showed the procedure on how to conduct the experiment 2, now I'm going to discuss the example of the results obtained in experiment 2. Now here is the table for both water-rich and the toluene-rich phase, which is for water-rich phase is the heavy phase, and for the toluene-rich is the light phase. We take the average value of the refractive index, and then we can calculate the percentage weight of the acetone by using the equation obtained from the water-rich and the toluene-rich phase graph. As you can see, the equation of water-rich phase from experiment 1 is y equals to 0.006x plus 1.3316, where the y is represented to the average refractive index and the x is represented to the weight percentage of the acetone. So when the average refractive index is y equals to 1.3632, therefore we substitute into the equation and find that the x is 52.73%. So in the table we have the 52.73%. So if you cannot follow, then we can make another example, which is for the light phase, toluene-rich phase. The average refractive index is 1.3587. So using the equation from experiment 1, the toluene-rich phase equation, y equals to negative 0.0024x plus 1.5076. Then when the average refractive index is y equals to 1.3587, then substitute the value into the equation and we will find that the x is equal to 62.04%. Then we do all the calculation and we summarize in a table. So for the water-rich phase, then we do all the calculation and we got the data, and the toluene-rich phase we do so and we got the data as well. Okay, now we are moving to the next slide, the equilateral triangle diagram. So here is the diagram. This is the triangular graph, and look at each of the vertices is represented by the solvent, the toluene, the diluent, water, and the solid acetone. For the water and acetone side is the water-rich phase, and for the acetone and toluene side is the toluene-rich phase. And we have the solubility curve from the experiment 1, and then we can plot our point for the toluene-rich phase first. So the first point is E1, the yellow dot in the graph, and for the water-rich phase is the R1, the raffinate. So we construct the 2 points and we join them by a tight line. After that, we do for the other point and we construct them with the tight lines. So after joining every point with the tight lines, and we can notice that the tight line for E1 until E4 are positive slope, and only for the last 2 tight line is having a negative slope. Next, we'll discuss about the error analysis. So the first error in the experiment is the low sensitivity and accuracy of measuring apparatus. When we're preparing the solution, we're preparing the acetone, toluene, and water mixture. We are using the measuring apparatus such as the burette and the measuring cylinder. The low accuracy, the low sensitivity of these measuring apparatus will lead to some errors in the volume of the mixture we prepare. After that is the high volatility of the acetone and toluene. As we know that the acetone and toluene are the organic solvent with high volatility, so that in atmospheric pressure and the room temperature, the acetone and toluene might have evaporated, so this results the volume of the mixture, the weight percentage of the acetone and toluene might have run a bit. The third error is the titration error. It is regarding to the cloud point. It's very hard to obtain a precise cloud point as the mixture keeps changing from colorless to cloudy. And this might lead to over-titration when the solution has first changed to cloudy. The over-titration is then will affect the result, so we must avoid this error. The error number 4 is the parallax error when taking reading. There is a possibility of the parallax error happen when we're taking the reading during the titration process. Number 5 is the calibration error of the refractometer. The calibration error during the calibration of refractometer, we must clean the refractometer first with the solution we will be testing in the refractometer. They might have some mistake on the refractometer, which the refractometer is not cleaned well, so that the refractive index that we obtain is not accurate. Finally, we come to the conclusion. So we conclude this experiment, the Equilateral Triangle Diagram experiment. The solubility curve is obtained experimentally by a cloud point titration. Second, a refractive indices decreases when composition of both acetone and water increases, while it is increased when the composition of acetone increases and the composition of water decreases. Number 3, the solubility curve is being separated into two regions, which are the upper region and the lower region. Number 4, the extract phase must contain high percentage of solute as compared to the raffinate phase. The tight line should be a positive slope in order for the extraction to work. So now have come to the end of our webinar.
Alright, here come to the end of the webinar.
I hope you enjoy watching it and learned something from it.
In this COVID-19 pandemic, things keep changing until we have to conduct the lab virtually without hands-on.
However, this is a new challenge for us and we must try to cope with it.
At last, thank you for watching our webinar. Stay safe and stay healthy at home. Thank you.